Hi everyone, welcome to lecture 19 of your electric circuit class. And lecture 19 is about storage element, and today is about inductor. The objectives for this lecture, the first one is to define an inductor and determine its voltage current VI relationship. And the second objective is to obtain the voltage waveform from a current waveform of an inductor, and the last objective here to obtain the equivalent inductance. So we are gonna go over these three objectives. So first, what we mean by inductor. Inductor is defined as a device that has the ability to store energy in its magnetic field. And it is usually a coil of wire. What about inductance? Inductance, it is, let's say, defined as the ratio of the voltage across the inductor to the current change rate with respect to time. And the inductance is measured in a unit called Henry, or simply H. So regarding the inductor voltage current relationship, we can say that the voltage across an inductor is V is equal to L multiplied by di over dt. So our V here, that is voltage in volts, this L here inductance in Henry, this I here is the current in ampere, and the T here time in seconds. So that's why when we defined the inductance, we said that current change rate, because it is di. So to obtain the current flowing through an inductor, we just integrate what? Integrate this equation here to extract that I. So in this case, our I is equal to 1 over L. The integral goes from an initial time t naught to t of V of t dt plus I of t naught. This I of t naught, that is the initial condition. So if we want to get the energy stored in an inductor, we can express it as W is equal to 1/2 Li squared. So this is the energy. So now look at V is equal to L di over dt. So for DC current, where it is not changing with time, which means that it is constant. So the voltage across an inductor is 0. This will give us that inductor acts as a short circuit to DC, because the voltage is 0. Because look at this here, if I is constant, then derivative of a constant is 0, and that will end up with that V to be 0, and the only condition that satisfies that V is equal to 0 is a short circuit. So that's why we are saying that the inductor acts as a short circuit to DC. So let us see how we can get, let's say, a voltage waveform out of a current waveform for an inductor. So let us do this example. So over here we need to find the voltage across a 4 millihenry inductor, and we need to sketch that current. Sketch that voltage. If its current waveform is as shown here, so this is over here is 2, this is 6, this is 8, and this is 10. And that time, let's say it's in millisecond, and this is our IL of t, and that is, let's say, in ampere, and this value here is 4. So this is the voltage, this is the current flowing through an inductor, and we would like to extract the voltage waveform, like to see how the voltage waveform look like. So when we do our solution here, we have to find the equation for this line, the equation for this line, the equation for this line, and the equation for this line. Because if you can see, this current from 0 to 2, it is 4 ampere, then it goes down from 4 ampere to 0 from the time interval 2 to 6, and then increase again to 4 from 6 to 8, and then decrease back to 0 for the interval 8 to 10 milliseconds. So we have to do these intervals. So we will start for t greater than 0 and less than 2, our IL of t is equal to 4. So this here is constant, going this way without any change, so it's a straight line and no change, then that will be 4. Now we go with the interval greater than 2 and less than 6. So we can write, this is how we do it. So this point here, that is 2 and 4. And this point over here, that is 6 and 0. So if I call this one, let's say x1, y1, this is x2, y2, and any point in that straight line, we can call it xy, and then we can go with the slope. So from this over here, we are gonna write, let's say y minus y1 over x minus x1 is equal to y1 minus y2 over x1 minus x2. So this is the slope equation. So in this case, that will give us y is any point minus y1, we said that is 4, divided by x minus x1 is 2. This is equal to y1 is 4 minus y2 is 0, divided by x1 is 2 minus x2 is 6. So we will just solve this equation over here, and that will be y minus 4 over x minus 2, that is equal to 4 divided by negative 4, and that is negative 1. So now we can say y minus 4 is equal to negative x plus 2, and from that y is equal to negative x plus 6. However, that our y, in this case, that is our IL, and the x over here is t, right? Then we can say for this interval from 2 to 6, our IL of t is equal to negative t plus 6. That is the equation for this line over here. Now we will go with the equation for this line. We will do exactly the same way to find that, and that will be for that interval. So we are gonna go for 6 to 8. So for t greater than 6 and less than 8. So that will be IL minus 0 divided by t minus 6 is equal to 0 minus 4 divided by 6 minus 8. And from that we will get our IL of t is equal to 2t minus 12. And for t is greater than 8 and less than 10, we are gonna get IL minus 0 divided by t minus 10, that is equal to 0 minus 4 divided by 10 minus 8. And from that we can say our IL of t for this interval is equal to negative 2t plus 10 plus 20. So now we can put that or these sets. It is 4 for t greater than 0 and less than 2, negative t plus 6 for t greater than 2 and less than 6, and then 2t minus 12, that is for the t greater than 6 less than 8, and negative 2t plus 20 for t greater than 8 and less than 10. So now we have our IL of t. We know that our VL of t for an inductor, that is equal to L di over dt. So what we need to do, we will just substitute the value of the inductance, and then we derive this equations with respect to t. So from that, we can write VL of t is equal to 4 times 10 to negative 3, since that inductance is 4 millihenry, and that is multiplied by the di over dt. So for the first one, the di over dt, so d of 4 over dt, that is a constant, so it is 0, and this is for t greater than 0 and less than 2. And then the second one, that is negative 1 for t greater than 2 and less than 6, and then that is 2 for t greater than 6 and less than 8, and then negative 2 for t greater than 8 and less than 10. So when we get that inside, like multiply that millihenry, which is 4 times 10 to negative 3, we will get those. That is, the first one is 0 for t greater than 0 and less than 2. And the second one is negative 4 times 10 to negative 3 for t greater than 2 and less than 6. Then we will have 8 times 10 to negative 3 for t greater than 6 and less than 8. And the last one, that will be negative 8 times 10 to negative 3 for t greater than 8 and less than 6. So this is, over here is our, let's say, current, our voltage equations. And then we can sketch that. To sketch that, we can do this. So if I have over here negative 4, over here negative 8, and over here is 8. And this over here is our voltage, and let's say that this is in millivolts, since we have the negative 10 or 10 to negative 3. So we will have this as 2, over here 6, 8, and 10, and that is time in milliseconds. So from 0 to 2, we have that to be 0, which is this. That is 0. Then from 2 to 6, I have negative 4. That is negative 4. So we bring this one here. This is 2. And then from 6 to 8, we have 8. So 6 to 8, that is 8. This is our 6 here. And then, so that is 6 to 8 is 8. And then from 8, we meant 8 to 10, negative 8. And this is our current, our voltage waveform for the inductor based on the given current waveform. So now we can go with the inductance or inductor connections. The first one, that is series connection. To find the equivalent inductance for a series connection of inductances, you will just add them together exactly the same as resistors. So that will be L1 plus L2 plus L3 plus Ln. It depends on how many inductances are connected in series. So this is how we can get the total inductance. For the parallel connection, again, it's exactly the same as our resistance connection. So 1 over L equivalent is equal to 1 over L1 plus 1 over L2 plus 1 over L3 plus 1 over Ln. Depends on how many inductors are connected in parallel. So for two inductors in parallel, we can use the formula L1 times L2 divided by L1 plus L2. So let us take an example here. So our example, we can go with, for example, this circuit. So we would like to determine the inductance L for the circuit shown if the equivalent inductance LAB is equal to 10 millihenry. And this is our circuit here. This is terminal A, this is terminal B, and this is our LAB, which is the equivalent, and that is 10 millihenry. So this is 3 millihenry, 2 millihenry, 8 millihenry, 15 millihenry, and this is the inductance we need to find, we don't know. And this over here is 2 millihenry, 5 millihenry, and 3 millihenry. So if you look at this circuit here, this is our solution. If you look at this circuit here, that is a short. So if we assume that we are gonna have a current flow in here, this current, it's going to split here and over here. So now when it comes over here, when the current comes over here, the whole thing gonna go through this short. That means really this over here is shorted out, which means that as it is not there. However, if you don't understand that, or you get confused about that, the best way is to redraw your circuit. So you assign nodes and redraw the circuit. So in this case, I have this as terminal A or node A. This is node B. I can call this node as, let's say, C. And I come over here, this is node D, and that is short. Then this is node D. That is the same node. So now we can, let's say, redraw the circuit. So this is node A, this is node B, and let's say this over here is node C, and this is node D. So now between A and C I have a 3 millihenry. So this here, that is 3 millihenry. Between node B and D I have L, that is B, and this is D, and this is L. Now between C and D I have 15. So this is C and this is D, and that is 15. Now between C and D I have 2 and 8 in series, that is 10. So this is C and this is D, and that is 10 millihenry. Now the only remaining is, or are these inductances, that is between D and D. So 3 of them, that is 1, this is the second, and this is the third, and it is between D and D. So whatever that you have in this circuit, if we inject a current, that current, it will just keep looping here. That means this here really we can take it out. It is not a problem because nothing is affecting the circuit. So now we can say our 10 parallel with 15, and that will be 10 times 15 over 10 plus 15. So that is 150 divided by 25. So 150 divided by 25, that is 6 millihenry. So now we have our circuit to be like this. Over here we have the equivalent to be 10 millihenry. We have this as a 3 millihenry. This is L, and this over here is 6. And all of these are in series. So when they are in series, we can say the equivalent is equal to 3 plus 6 plus L. So from that, our L for sure is equal to 1 millihenry. By this, the lecture is over. So I would like you to pay attention to the following. For a current flowing through an inductor, it cannot change abruptly. What that means? It means if I have this as I of the inductor, then the current, it can increase and decrease. So this over here is okay because it takes time to go from one value to the other, and then it takes time to go from that value to here. So this here is okay, like as a waveform. But this here, We cannot say that it will increase that way and then it will go back to 0 from this point to this point. So it's going from a value to, for example, a 0 in no time. That is not allowed. That is not a behavior of inductor current. And then if you know how to find the equivalent inductance, and then how to obtain the VI relationship, you will be in great shape for this lecture. Our homework for this lecture is this: 2 problems. If you know how to solve those, I believe that you will be, as I said, in good shape. Thank you for watching.